Okay, we're picking up on page 531. This is section C. We're going to be talking about the derivative function. So for a nonlinear curve, the general one, y equals f of x, whether it's the parent function of a quadratic, or if it's x cubed, or x to the fourth, whatever it is. So here's the general way to write that. And the gradient of the tangent to this nonlinear curve or function is going to change as m gets closer and closer to f. And so what we want to do is we want to figure out, so how do we write a gradient function? In other words, a function that no matter what value of x we plug in, it's going to tell us what the gradient of the slope is, so we don't have to go through all of the long mess of trying to figure it out a different way. So this function, the gradient function, is called a derivative because it's derived from whatever f of x is, whether f of x is one of these or something different, or whatever it is. Now the process of finding the derivative function is called differentiation. And when we find this derivative using limit theory, we say that we're performing differentiation from first principles. So let's look at a little bit of what this would look like. And let's just start from the basic parent function. But before we do that, I want to walk you through something. And this is actually on page 531, number 3 in your textbook. You should have done this for homework, but we're going to walk through it quickly. So let's just put a little table together. And this is our x and our y values. And we're going to do this for the basic parent function. So let's say y equals x squared. And this is going to be our gradient. So again, as the x values change, then our gradient is also going to change, the gradient of the tangent. So let's plug in, let's start with 1, and we've already solved for 1 before. That's our f point that we've been using, 1, 1. We said the gradient there was 2. So let's go through and let's solve now. Let's just do 2 more points, and I want you to see the pattern here that's happening in terms of the relationship between the x value and the gradient. So when we plug in 2 as our x value, our new f will be the point 2, 4, and we got that just by using 2 for x, and then we plugged it in because the y value is the function of x, so we plugged it in and we got 4. That means that our m value is going to be 2 plus h, and then it's going to be the function of 2 plus h, so we plug in 2 plus h, and we come out with 2 plus h squared. Now we can go through the process and we can do y of m minus y of x over fm minus fx. And we should find something like this. We get h squared plus 4h plus 4 minus 4. That was these two, over 2 plus h minus 2, and that was these two. So now we can cancel these out, and we can also factor out an h, and we're going to get h times h plus 4 over h, which leaves us with the limit as h approaches 0 of h plus 4 equals 4. This is our gradient for this point. Now, we're going to do that just one more time, and I think what you'll see if you take the time to work it out is that you're going to come out with a 0.39. When we plug in 3 for x, it gives us 9, which means then that our gradient, again, if you go through and work it all out, our gradient is going to come out to be 6. So what is the pattern or the relationship between the x value and the gradient? Well, you can see that each time the gradient goes up by 2, but there's another way that we could write this pattern, you could think in terms of arithmetic sequences if you wanted to. That might be helpful. Or geometric sequences. So let's just look at it and see what's happening. So we have x value of 1 and the gradient equals 2. Well, what is happening? Well, we could say that we're adding 1, but I don't think that's it because it doesn't hold true in the next piece of it. So I think the better way to write this is that 2 times x equals the gradient. And that pattern, if you kept working it out, that pattern would continue along the way. So what we can do then is we can write a derivative of our parent function, and that is 2x. So f prime of x equals 2x. And we would say that this was performing differentiation from first principles because we used the limit theory to come up with this particular derivative. Now let's look at another example, and I think this will make a little bit more sense even to you guys. So we want to find f prime of x given that f of x equals x to the 4th. Now the way that we're going to find this, we could find it, we could probably surmise and deduce by doing our table of values like we did just a minute ago. But I think there's a better and quicker way to do this. So let's take a look. So what we do is using what we've generalized before, we had the point f is x and the function of x. The point m then is x plus h and the function of x plus h. Now let's use our slope formula and plug in what we know. So f of x plus h minus f of x over x plus h minus x. Now when we do that, really as far as we can get here is we can cancel out these x's, and so we're left with f of x plus h minus f of x over h. And this is the gradient of the tangent at this generalized point. So now let's go through and let's work this for our current plan. So we had f prime, so f prime of x, and we're using the function f of x equals x to the 4th. So what we would say is f prime of x equals the limit as h approaches 0 for f of x plus h. And right now all we're doing is we're just rewriting our formula again over h. And this is the formula that we just came up with. So now we just plug in values. So when we take x plus h and we put it in here, we're going to get x plus h to the 4th. And then when we plug in x, we're just going to get x to the 4th. And all of that is over h. Now, probably the simplest way to work this piece out right here, if you guys don't remember Pascal's triangle. Pascal's triangle is what I would recommend that we use here rather than just working out by hand x plus h to the 4th. So I think you guys will find that that will save you a little bit of time. So we can remember Pascal's triangle looks something like this. And we'll go to the 4th, so we want to get all the way down to the 4th row. So here it is. Now, let's see, how do we work this? So, well, these numbers are going to be our coefficients. So let's go ahead and start these out. So this is going to be 1x to the fourth plus 1x to the third h, excuse me, not 1, that should be 5, plus 8x squared h to the second plus 5x h to the third plus 1 h to the fourth minus x to the fourth, that whole big ugly thing over h. Now, there's really not a whole lot that we can do here. There may be a couple of things. So let's cancel out. So we can cancel out this x to the fourth and this x to the fourth, which leaves us again with a really big ugly thing. 5x cubed. Now wait, all of these have an h in common. So I suggest that we take out an h off the bat here. Let's do that, because then we have an h in the denominator, we can cancel that out. So in that case, then this would not be 5x cubed, this would be 5x squared, and the h will be gone, plus 8, excuse me, that will be 5x cubed, but the h is gone, plus 8x squared h plus 5xh squared plus h to the third. I think I did that correctly. Over h. Now those two will cancel out. And now what are we going to do from here? Well, this is really as far as we can go in terms of simplifying. So let's just do the limit as h approaches 0 of this whole thing. So in other words, we're just going to plug in 0 for x, or h, excuse me, and let's see what happens. So this one is going to cancel out. It's going to be 0. This one is going to cancel out and be 0. Also, this one will cancel out and be 0, which leaves us then with 5x cubed. Which, okay, going back here, you guys are looking at me like I'm crazy because this should be a 2 here instead, which means these are all 3's. And so this, instead of being 5, that's my fault, these 5's should all be 4's instead. That's 4, and that's 4x cubed. So f prime of x, yeah, there we go. That makes a lot more sense. And so here's our derivative. We have differentiated from first principles because we used the limit theory. Okay, guys, I hope that makes a little bit of sense to you, and we should be able to go from there. So now the next part of the question then is, if we wanted to find f prime of x at -1, well, all we would do now is just plug in -1, and this is a whole lot easier. Wow, it's a whole lot simpler to solve. So this 4 times -1. So the gradient at this point, or when x is -1, so we could go through and, wow, if we wanted to make a table at this point, we could make one pretty quickly. So we would plug in for x value -1, and we would know right off the bat that the gradient is going to be -4, and we could do any number of values that we wanted to. Much quicker and simpler.